Okay. Hey guys, Matt Young here with Flowco, and today we're going to get started with another e-learning series. Today's e-learning series 4, talking about flow path guidelines. So understanding, should we select tubing flow, annular flow, or hybrid flow, depending on the well type, well characteristics, and production. So that's what today's topic is going to be about. So really, as always, guys, if you have any questions, we've got the chat function available. Just throw in a question there. We can stop and answer it during the presentation, kind of keep on going. But ultimately, what we want to talk about today is picking the right flow path for your well. And there's a couple different ways to look at it. Primarily, what we'll talk about today, though, is picking your flow path specifically to maximizing production or minimizing flow and bottom hole pressure in reality. So that's kind of the main purpose, is like, what is the best flow path to put in the well today to help maximize the production out of the well, to achieve the lowest flow and bottom hole pressure, those type of focus points. So, but of course, anytime we're dealing with larger flow paths, 3.5-inch tubing, 4.5-inch tubing, or maybe annular flow, one of the things that we do have to consider with unconventionals is eventually we're going to have to reduce our flow area, or we're going to have to switch our flow path. Primarily because the unconventional wells are ever declining. So maybe that larger tubing size or larger flow area helped us early on in the well, when production rates were high, to help stabilize that large flow area. But production rates have declined over time. We're starting to see some instability, some slugging or heading of the well. And the way to optimize that, to reduce that instability or slugging, is really to reduce the flow area. So, when do we switch? How do we tell when we need to switch from a large flow area to a smaller flow area? So we'll definitely touch on that. And then the last thing I kind of put together was some guidelines to look at in terms of production rates. If we expect this much production, what's a good rule of thumb? What's a good guideline to pick our flow path area? So those are kind of the topics I want to touch on today, go through with everybody and really dive into it. And then lastly, all these trainings we'll record, post up on our website. You can find on YouTube as well. So if you missed a presentation, if you want to go back and critique my presentation or anything like that, you can find that on the Flowco website. And then also if you subscribe to the Flowco YouTube channel. So with that, guys, we'll go ahead and get started here. So pull up some information that wanted to talk about today in terms of really picking those flow paths. So let me go back. Apparently I was looking at this earlier. So what we're looking at here is flow path guidelines. So again, like this presentation is focused on, it's primarily focused on guidelines for picking your flow path. Meaning, things like, if we can casing flow the well initially, when should we install tubing into the well? Should we install tubing into the well after completion, depending on the production rates? Should we let the well casing flow or natural flow up the casing for a period of time and then come back and install tubing at a later date? And the idea behind that is, one, to maximize the production through the flow into the casing, and then also to prevent any kind of production restrictions or flow and bottom hole pressure increases by simply just installing tubing in the well. And again, one of the things that I'm going to focus on in this guideline is primarily focused on maximizing production or achieving the lowest flow and bottom hole pressure. So if that's not your end goal on a new completion well, then your guidelines are pretty easy. Put small tubing in it, choke management, and then let it flow for extended period of time. But if you're an operator that's trying to maximize the production out of a new well, or trying to achieve the lowest flow and bottom hole pressure, then these guidelines and flow path selections really come into play to help us understand what's the best flow path large tubing, annular flow with small tubing, some of the different applications there, again, to maximize that production and achieve the lowest flow and bottom hole pressure for either naturally flow or a gas lift well. And then really one of the big things with that too is also, when do we need to convert? Eventually we're going to have to convert from a large flow path to a small flow path, or smaller flow path, I should say. And when is that in terms of like production rates, identifying instability, maybe turning on gas lift if this is a gas lift well. Really dive into a lot of those things, again, to try to reduce that heading or slugging, try to improve the stability of that current production. So really things I wanted to share with you guys today, and really go over these topics. So a few things to touch on is anytime we're looking at flow path review, or I guess I should really say more of like hydraulics review, one of the biggest key components within all that is understanding your multi-phase flow correlation. So that multi-phase flow correlation helps calculate those pressures throughout the wellbore based off of that flow area that we define for the well. And so making sure we have an accurate multi-phase flow correlation is incredibly important because it can show us what our flow and bottom hole pressure would be under different flow areas. It can also show us like when we may experience instability within the well based off those production rates. And so it's always good to go back and confirm you have, or you're using the right multi-phase flow correlation. A couple ways to do that. Of course, like a flowing pressure temperature survey is going to be the ideal way to do it, because you're going to be able to get that pressure gradient throughout the wellbore. If you have a downhole gauge in an offset well or the well you're interested in, you can also grab that downhole pressure from that gauge and correctly select that multi-phase flow correlation. So one of the things I always like to start with is that we need to make sure we have our correct flow correlation. I will say that, hold on, I'm going to jump ahead for a second. I will say that typically, like a good guideline for flow correlations, primarily for like lower 48. And of course, this doesn't cover all wells in all areas, but just kind of generalizing here, is for tubing flow, 3.5 inch tubing or smaller. Hagedorn and Brown is a typically relatively safe flow correlation. Again, just kind of generalizing here. And then for larger tubing sizes, bigger than 3.5 or annular flow, Ansari seems to be a pretty good flow correlation. So if you don't want to implement the time and the money to collect the data to pick a flow correlation, Hagedorn and Brown and Ansari is going to do a pretty good job for a bulk of the wells. But again, the main thing is data collection on one or two wells under similar conditions and like benches that you're producing out of to just make sure you pick the right flow correlation. So when we talk about flow area, we have some pros and cons with the unconventionals. One of I'll start with the con. We'll start, the compliment sandwich here, is that one of the cons is most of the time we're going to be confined to pretty small wellbore, meaning our casing size is going to be relatively small. 5.5 is going to be a pretty common one, maybe 20 to 26 pound. Maybe we're lucky and we can find a couple wells with 7-inch casing, but generally wise, 5.5 is going to be typically our flow area. The con to that is it's hard to get big tubing in a well that has 5.5-inch casing. Like your best case, you're going to be able to put 2 7/8. If you go and really convince your completion or your workover foreman that you can put 3.5-inch tubing in your 5.5-inch well and be able to fish it out later on in life, maybe you can get 3.5. But usually with 5.5-inch casing, you're going to be confined to 2 7/8 tubing or smaller. So that's kind of the con. I'll go back to the compliment sandwich. One of the benefits to 5.5-inch casing is it acts as a really good flow path during initial completion, meaning that after you drill out your frac plugs and you clean the well up, you can naturally produce the well of 5.5-inch casing, and it tends to do a pretty good job of stabilizing production, especially when you have the reservoir pressure and the formation gas volumes. Now, if you're one of the lucky few that have 7-inch casing or larger, then the kind of the world's the limit at that point in terms of your tubing size. You can run 3.5, 4.5, 5.5-inch production tubing, so you get a wide variety of flow path selection with 7-inch casing. But what I wanted to kind of illustrate here is some of the different flow paths. So for tubing flow, common ones are going to be either 2 3/8 tubing, 2 7/8 tubing, or 3.5-inch tubing. And then some of the common flow paths for annular flow, 2 3/8 tubing inside 5.5, flowing up that tubing casing annulus. Of course, 2 7/8 tubing inside 5.5. And then for the more adventurous folks, 2 7/8 inside 7-inch or 3.5-inch tubing inside 7-inch as your annular flow. And with that, I listed out some cross-sectional areas just for a comparison. So, when we look at 2 3/8 tubing, that cross-sectional area in square inches is a little over 3 square inches. And then if we look at, say, 2 7/8 inside 5.5, it's almost 12 square inches. So it's almost 4 times as large as 2 3/8 tubing. So you can kind of see the benefit of going annular flow in some of your higher producing wells because of that increase or that incremental increase in cross-sectional area. One thing to note, though, about cross-sectional area, especially in annular flow, is it's very easy to get a equivalent flow ID, meaning that you take your cross-sectional area in square inches and then just convert that over to pipe diameter. But one thing that I do see in the industry is that equivalent flow ID or pipe diameter isn't necessarily the correct equivalent flow ID that you should use when you're reviewing annular flow wells. And the main reason for that is the pipe inside pipe flow path, meaning that if we look at our little donut over here on the left, we have casing on the outside circle, production tubing on the inside circle. And so if we flow up this donut area, one of the things that you'll notice is we're increasing our surface area or our surface area that we're wetting with flow. And so by doing that, we increase our frictional pressure loss through that wall wetting, which then reduces our equivalent flow ID. So just something to note that if you take your cross-sectional area, convert it over to pipe diameter, that's not going to be a very accurate reflection in terms of what your equivalent flow area would be if you were to do annular flow. Historically, what I find is that whatever this equivalent flow area is, depending on formation gas rates, that can, and liquid rates, water fraction primarily, that can be reduced by up to 1/2 inch. Meaning that if we use, let's just easy math here, a 5.5-inch equivalent flow area for 2 7/8 inside 7-inch, that's really going to be like 5-inch or maybe even a little less than 5-inch in terms of true flow ID based off of that frictional pressure loss with that additional wall wetting. So something just to consider if you're one of the folks that like to just take equivalent flow area. So when we look at this, these are kind of the flow paths that I want to talk about today. There's definitely more out there. These aren't the only options you can do, but these are going to be the most common applications that we see. So when we talk about well types, especially for this guideline here, I wanted to kind of post up some of the well types that we utilize to create these guidelines. And I broke the categories up into a few different pieces. And primarily the pieces that I found had the biggest effect in terms of maximizing flow and bottom, or maximizing production rates, minimizing flow and bottom hole pressures. And the things that we found were kind of the key drivers. Of course, one of the big ones is reservoir pressure. And I broke it up into essentially high and low. So 6,000 PSI or greater, less than 4,800 PSI. It's kind of the two ways I noted it. And I'll give you some pointers on this. So what we found with reservoir pressure is flow path area or restriction of flow path meant less when you had higher reservoir pressure and became more important with lower reservoir pressure. The reason for that, I think, is with your higher reservoir pressure, you can overcome a lot more frictional pressure loss because you have that additional reservoir pressure. Whereas when your reservoir pressure decreases, you can't necessarily overcome that frictional pressure loss with reservoir pressure. One of the big key takeaways we found when it came to two things. One, of course, picking our correct flow path. And secondary to that, when do we convert? We found that total GLR, TGLR, and for anybody that's unfamiliar, GLRs are gas to liquid ratio, is as your GLR or total GLR increased, the time between conversion extended as well, and you were able to flow at much greater rates in a much larger flow area. So we found that TGLR, and I call it TGLR because that could be formation gas and injection gas for gas lift well, had a huge effect on pick and flow areas. Meaning that if we had a high TGLR greater than 1,000 to 1, we wanted to get the largest possible flow area, which helped further drive down our flow and bottom hole pressure in our production. If we were playing in wells that had a relatively low TGLR, less than 1,000, then we wanted to be very careful on our flow path selections. And you'll see here in a few slides how I illustrate that. But what we found is that with low formation GLR wells, you wanted to select a smaller flow path to help stabilize and maximize that production. And then ultimately, the other thing that's going to have a driver on our flow path outside of our reservoir pressure and our TGLR is going to be, of course, our total liquid rate. So higher liquid rates, larger flow area, smaller liquid rate, smaller flow area. So pretty easy on that one. But some of the things I wanted to reference, we'll see some of these notations when we look at our different flow types and our different well examples that we use, such as higher low reservoir pressure, higher low TGLR, 1,001 plus or less than 1,001. And then same thing, high to low liquid rates, greater than 2,000 barrels per day, and of course less than 2,000 barrels per day. So a couple little key notes to look at. I might jump back to the slide too as we kind of go through that. But these are kind of the big takeaways, really good lessons learned that we found with this, this project. So let's look at some graphs now, and we'll spend the rest of the time kind of looking at some of the different graphs that are out there in terms of production rates and things like that. So one of the first well types that we used was a high reservoir pressure, high total or FGLR for formation GLR, and high liquid rates. So we had the high of everything: good reservoir pressure, good formation gas or good total gas, and relatively high production rates. And what we find here is that each one of our hydraulic models, starting on the left in red and going all the way to the right in blue, was a change in flow area. And so, of course, the one on the left in red is 2 3/8, followed by 2 3/8 tube inflow, followed by 2 7/8 tube inflow in green, and then followed by 3.5 inch tube inflow and call it light blue. And then from there, 2 7/8 inside 5.5 annular flow, and then pinks 2 3/8 inside 5.5 inch annular flow. And then the green is going to be 3.5 inside 7 inch annular flow. And then ultimately kind of capped off with 2 7/8 inside 7 inch annular flow. So when we are dealing with high reservoir pressure, high GLR, high flow rate, the best way to achieve the highest production rates, the lowest possible flow and bottom hole pressure, is to get the biggest flow area we possibly can. So if we're playing inside 5.5-inch casing for this well type, maybe the best thing is to naturally flow it up casing for a period of time. And then when we are ready to tube it up with 2 3/8 tubing, which then achieves a production rate of about 9,000 barrels per day and about a 2,000 psi drawdown. If we're one of the few that has the benefit of running 7-inch casing in the well, then of course 3.5 or 2 7/8 annular flow is going to be the best option, with a production rate of like 11 to 12,000 barrels per day and a drawdown of 3 to 4,000 psi, less than reservoir pressure. So you can see that your well type or your casing configuration is going to have a big effect on this overall production. So like what this tells me is that if my well's capable of producing these rates, which, you know, a well like this is probably going to be a Delaware Basin well over in New Mexico, is that maybe 7-inch casing, again, depending on completion type, might be a good option, or possibly 5.5-inch casing with plans to casing flow the well initially and then tube it up with 2 3/8 tubing, or very small tubing, to help maximize that production. Another way to quantify this is to look at production rates on our y-axis versus flow area on our x-axis. And of course, this one looks very linear, meaning that as we increase our flow area, we're going to get an equivalent production increase as well. Now, eventually, this would probably taper over once we start to get into some of the casing flow sizes. But when we're looking at picking our tubing size, we can see this one's pretty linear, meaning that if we have good reservoir pressure, we have good formation gas rates, the bigger the flow area, the better. And what we'll find too is as we begin to tweak some of these different configurations, we'll see that not all the time bigger is better, right? And so in this case, we have 2 of the 3 components to make a big flow path the best selection. So we have decent reservoir pressure, high reservoir pressure, and higher liquid rates. But one of the things that we're lacking in this well type is relatively high formation GLR, total GLR. So, less than 1,000 to 1 GLR. And so one of the 2 things that we notice is, of course, our overall deliverability in terms of production is less. And again, very similar, starting with 2 3/8 on the right, ending with 2 7/8 inside 7-inch on the 2 3/8 on the left, sorry. 2 7/8 inside 5.5 on the right. And I work in that, kind of process, because if we were to go back and look here, 2 3/8 is going to yield the smallest flow area in terms of cross-sectional areas, square inches. And then 2 7/8 inside 7-inch is going to yield the largest cross-sectional area in square inches. So we have 3 square inches for 2 3/8 and all the way up to 23 square inches for 2 7/8 inside 7-inch. So you can kind of see that progression from 2 3/8, 2 7/8 to 3.5, and then our different flow areas for annular flow. So what we find is when we compare our hydraulic models for those different flow paths, our production incrementally increases as we increase our flow area, and our flow and bottom hole pressures decrease as we go through that. So kind of see that progression as we work down. One thing you'll note too is that as our formation GLRs decrease, the delta between maximum production and minimum production really tightens up. It becomes a lot less. And again, the big driver we found in this project was that GLR, that total GLR, formation GLR, had a really big impact on that. And we'll look at it on the next slide here to see how our flow areas don't necessarily have the same benefit as we increase our flow areas to maximize our production. So of course, as we increase our flow areas as indicated on our x-axis, we do get more production out of the well, but we don't get it incrementally as much as we did if the well had a higher formation or higher total GLR. So things to note here in a case like this, maybe not maximizing our flow area is a great idea to achieve the best or the most stable production on the well. Maybe picking 3.5 inside 7" instead of 2 7/8 inside 7", or maybe picking 2 7/8 inside 5.5 for annular flow versus 2 3/8 inside 5.5, as our previous example illustrated. So you begin to understand that as things like our formation GLR, as our reservoir pressure, as our rates change, this flow path selection changes as well. So let's look at another well. You can kind of see we're working our way down our legend here. So the next one is good formation GLR or total GLR, but we're met with a lot lower rates. So maybe this is a Eagleford well or Austin Chalk well, or maybe it's not those big wells that we see over in the Permian and Delaware Basin, but we still need to focus on maximizing production. And of course, very similar progression, 2 3/8 to the left, increasing our flow area as we work down our deliverability curve. But again, as those liquid rates or those GLRs change, our production difference or delta production tightens up quite a bit. And this one we find if we look at our comparison of flow area versus liquid rate, we definitely see that we hit a cap when we get around our 2 7/8 or 2 3/8 inside 5.5" annular flow. In a case like this, any type of annular flow, if we had 7" casing, would not be ideal because we could actually hinder production just due to liquid holdup and liquid loading of the well. So in a case like this, if we were presented with 7" casing, then we might pick 3.5" tubing as our flow path. If we had 5.5" casing, then we may consider either 2 7/8 or 2 3/8 annular flow inside that 5.5" casing. Because really anything larger than 2 3/8 inside 5.5 cross-sectional area would hinder production and not help us maximize that production. So something to note as we begin to manipulate our GLRs, our liquid rates, things like that. And then kind of the last one is, worst case, right? Low formation GLR and low liquid rate. So not a very good dynamic flow well, meaning that one, it probably shouldn't be on gas lift, probably should be on ESP or rod pump, maybe jet pump, something like that, because we're met with both low GLR and low liquid rates. And this one, I'll jump ahead to the next slide to talk about it for a minute. This one, we can see that maximizing our flow area would actually hinder the production of the well, meaning that going past like 2 7/8 tubing would not be a good idea for this well type because we would encounter so much liquid loading and instability that we would artificially increase our flow and bottomhole pressure and prevent the maximum drawdown, the maximum liquid removal out of the well. In reality, this one probably shouldn't be on dynamic form of artificial lift such as gas lift, but if you were to put it on gas lift, 2 3/8 or 2 7/8 tubing would be your ideal flow path, meaning a very small flow path for this well type. So things to consider when we're looking at our different flow areas. Best way to understand this is kind of twofold. One, always good oil field rules of thumb and experience after you brought a couple wells online, understanding the well types and your flow areas. Secondary to that, and a more preferred method, is having some program that can help build hydraulic models out. Hydraulic multi-phase flow models. That can be as simple as a Excel program if you have somebody in-house that can build that, or there's a ton of commercial softwares out there, such as like Prosper, Snap, Wim, just to name a few, AppSmith, that can build these hydraulic models for you. So preferred method is, of course, to run those hydraulic models, but then you can always revert back to the good old oil field rules of thumb. So the next thing that I like to look at is conversion. If we do plan to go with the largest flow area, when do we need to switch? Meaning, when do we need to reduce that flow area to help stabilize that production? Knowing that these wells will decline in production eventually, we need to plan for instability as that production decreases, and we need to plan for a reduction in our flow area. And this could be as simple as switching from maybe annular flow to tubing flow if you planned out your completion and had a hybrid system in place. If you only ran an annular flow system, then that might result in having to pull tubing to convert over to tubing flow or reduce that flow area. Maybe you have a very big tubing size in there and you simply just need to lay down that large tubing and replace it with a smaller tubing string. So a couple different ways to look at changing that flow area to help stabilize that production. When do we need to convert? A couple ways to look at it. One of the most simplistic ways to do that is just to monitor existing flowing pressures and production rates. As you begin to see your instantaneous gas rates change, as you begin to see your tubing or your casing pressure fluctuate, that's typically an indication of instability or loading or slugging heading of the well. And all those things can be driven by too large of a flow area for the production rates that the well is currently producing. So in a case like that, that can be a very good indication to make that conversion. Another thing that I find is that you can do a historical look back at conversion rates for previous wells and make that conversion or set a KPI in terms of that conversion rate for things like barrels of liquid per day typically. So what we find in certain areas is that a lot of times annular flow inside 5.5 to 2 7/8 tubing flow, that conversion typically occurs between about 1,000 and 1,500 barrels per day. In other areas, that conversion rate might be 600 to 800 barrels per day. So you tend to find conversion zones based off of the basin, the formation that you're typically operating in. So another thing we can do is you can run nodal analysis to model that instability. You can run those hydraulic models to understand that. So if we go back to our first example here, higher formation GLR, higher liquid rates, because of that formation GLR is so high, or that total GLR is so high, that we can look at converting from, say, annular flow to tubing flow around 1,500 barrels per day. And once we achieve that 1,500 barrels per day of total production, water and oil, we can look at converting from annular flow to tubing flow. Now, of course, if we just installed large tubing in this well, say like 3.5-inch tubing, then we can look at converting from 3.5-inch tubing down to, say, 2 7/8, around 500 barrels per day. And again, what we found was that formation GLR, or that total GLR, was a real big driver in terms of that conversion rate. And what I mean by that is as our TGLR, as our GLR decreases, so we begin to lower that total GLR, our conversion rate or our conversion time increases. So if we're dealing with a higher liquid rate but a lower GLR well, then that annular flow to tubing flow conversion zone begins around 2,000 barrels per day, meaning that we don't have the formation gas to help stabilize that flow. And then same thing for tubing, so 3.5-inch tubing to, say, 2 7/8, instead of 500 barrels per day, we're now having to convert between 1,200 and 1,500 barrels. So you can see that as our GLRs decrease or increase, that conversion time or that conversion period changes as well. So the way I like to look at it is the higher GLR you have, the longer you can flow it under that large flow area. The lower that GLR is, the shorter period of time you can flow under that large flow area before you need to convert. And then, of course, like with lower rates, lower GLRs, then we need to convert in a very short period of time, meaning that our benefit of annular flow is going to be pretty small, or it's going to be a very short window of time before we have to convert. So one of the big things that I take away from that conversion zone, there's really kind of three primary ways to identify that. Look for that instability or heading of the well and make that decision then. Pick a production rate based off of historical production and make that conversion then, or run that instability calculation or model through a hydraulic nodal analysis program to understand when that conversion is going to be. One of the other things that I wanted to put together with this was just a really helpful compatibility table, meaning that if we have a general idea of production and TGLR, what's the best flow path for that well type? And so, how we find production and GLR, maybe we look at a type curve, at a forecast provided by reservoir, maybe we look at historical production from offset wells, but we pick an ideal production rate that we expect out of the well initially. And then with that, we can then kind of work down our compatibility table to understand what's the best flow path. Again, if we're wanting to maximize production, drive that flow and bottom hole pressure down as low as possible. So, when we deal with our annular flow cases, and again, this isn't all of them, this is just going to be the most common ones, 2 7/8 inside 5.5, 2 3/8 inside 5.5, 3.5 inside 7-inch, and of course 2 7/8 inside 7-inch, kind of your most common annular flow applications. In a case like this, really any type of well that we expect to produce 4,000 barrels or more, all those selections are going to be great in terms of handling that production rate, minimizing that flow and bottom hole pressure. Once we get into like 3,000 barrels per day, sub 4,000 barrels, your really large flow paths, meaning your 3.5 inside 7-inch or your 2 7/8 inside 7-inch, might not be recommended. And the main reason for it is early on, they would be able to flow in a stable condition, but it's not going to take much production change, maybe 500 or 1,000 barrels per day, to take a relatively stable well and move it into the unstable category. So if you plan to put small tube in a big casing or maximize your flow area, then kind of the note is have a plan to convert or switch to a smaller flow area once you get around that 3,000 to 4,000 barrels per day. And then, of course, if you're, in most cases, if you're sub 1,000 barrels per day, annular flow is probably not your best choice. Probably going to tubing flow is going to be your best choice to maximize your production rates, minimize your flow and bottom hole pressures, and keep the well on stable production. And then, of course, if we drop down to our table below, we can look at very similar compatibilities for tubing flow, 2 3/8, 2 7/8, and 3.5-inch tubing. And in a case like this, with 3.5-inch tubing, we can produce relatively high liquid rates without any kind of detrimental frictional pressure loss. Now, of course, once we start creeping up over around 6,000 barrels per day, friction does like to take over at that point, and hopefully we can offset that with some reservoir pressure. If not, we might hold back production or increase our flow and bottom hole pressure at those really high rates. Very similar to the high rates, as our production rates decrease with 3.5-inch tubing, we do need to make plans to convert, meaning that maybe we have to pull that 3.5-inch production tubing and downsize to 2 7/8 or 2 3/8. Or if it's a gas lift well, then maybe we have to increase our injection gas rates to help stabilize that production, because our liquid production isn't there to fill that void or that flow area. So things to consider. Really, I found this table helpful in terms of picking production rates and GLRs against your ideal flow path. And again, this whole table is focused on maximizing that production, minimizing frictional pressure loss, and reducing our flow and bottom hole pressure as much as possible. If you're only looking for stability and maintaining reservoir pressure, then the answer is always going to be the smallest tubing possible that you can get in the well. But if you're trying to maximize production, reduce any kind of frictional pressure loss, we go the other way. Larger flow area, typically matched to our production rates, is going to be ideal. Couple lessons learned we found working on this project with a couple of operators is TGLR, or our gas to liquid ratio, really had the biggest effect on picking flow areas. One, just simply for flow area selection, and then two, time period to convert to a smaller flow area. And so what we found is that the higher the GLR, the larger the flow area you initially want to start with, and the longer period of time or the greatest range of production rates you can flow the well before needing to convert over to a smaller flow path. Of course, lower GLRs had a negative effect on large flow paths, so really keeping that in mind. Other things that we found, of course, as your reservoir pressure decreases, your production rates are going to change, and we need to really size our flow areas based off of those production rate changes and our reservoir pressure change. And so that's what we kind of illustrated here in our scatter plot, is different flow characteristics in terms of reservoir pressure and GLR. And you can see that if we have the benefit of high reservoir pressure and high GLR, our span between flow areas and production rates range from 3,000 barrels per day up to 12,000 barrels per day. So a really big span of production capabilities if we have reservoir pressure and formation GLR. Of course, if we don't have reservoir pressure and we don't have GLR, then that span from 2 3/8 tubing to annular flow could be less than 2,000 barrels per day. So it could be a very small production increase as our reservoir pressures decrease and our GLRs decrease too. So things to look at. Really good lessons learned here. Definitely found that this is something that we can build on and really improve on in terms of flow path selection. But the biggest takeaways are, look at our production rates, look at our total GLRs, and that might just be formation GLR, or it could be a combination of formation and injection if we plan to gas lift the well, to really help pick those flow paths. And then, of course, always have a plan to convert from a large flow path to a small flow path, because if you're playing in the unconventional world, eventually you're going to need that plan or that time period to convert from a larger flow path to a smaller flow path. The reason for that is if it's on gas lift, you're going to want to allocate that injection gas rate to maybe a newer well. And then, of course, if you're running into any instability, heading, slugging of the well, then you're going to want to reduce that flow path to help restabilize that production, help that well from liquid loading. So, guys, a couple other things to note too about future trainings. We have plunger assisted gas lift coming up, how to select, how to calculate, how to identify that here in a couple weeks, followed by some capillary tubing downhole gauge discussions, plunger lift, and then waiting on some wild card presentations to come out there towards the end of the year. But with that, guys, I will answer some of the questions that came up, and we'll go ahead and wrap it up for the day. So, guys, a couple things that came up, during this discussion is, of course, when to switch from annular flow to tubing flow. Biggest question that we see, a very important question. My general response to that is when we begin to see instability, especially instability so bad that it begins to affect facilities, affect compression, even possibly like ESD our wells based off of that pressure swing. Best idea to switch. So from large flow area down to a smaller flow area. Another question we got in terms of flow rates for your different flow paths. So generally speaking, if we're greater than about 1,500, 2,000 barrels per day, we should consider annular flow depending on our casing size. Yeah, generally speaking, if you're less than 2,000 barrels per day, tubing flow is probably going to handle your production better. There is a little caveat to that for those really low reservoir pressure areas. Annular flow tends to be the best application just to help maximize that drawdown and keep the wells on production. And the last one was how do we select our best flow path? That goes back to a few things. One, of course, is just general field experience in that area, what offset operators are doing, what the operator has seen in the past in terms of best production. Ideally, outside of that, it's going to be a good hydraulic modeling program. Any type of nodal analysis program that's going to allow you to build your hydraulic models, meaning your flowing pressure of the well with flowing bottom hole pressure to help predict which one's going to lower your flowing bottom hole pressure the best and keep the well on production. So I would recommend finding a good hydraulic model or finding a vendor that has a good hydraulic model that can build those cases for you. Guys, that's it for today. I do appreciate you guys getting on. Of course, we'll post this on YouTube so you guys can go back and watch it there. If you have any other questions, always reach out to us. If you have any complaints or critiques of the presentation, let me know. Always open ears to make changes. And other than that, thank you for joining, and we'll see you next time.